Today again it is the second lecture of stereoisomerism. In the last class we had discussed what is stereoisomerism, what is GI, what is geometrical isomerism, what all different in what all different conditions GI can occur. We discussed about carbon double bond carbon and ring system cases. Now in today's class we will understand GI due to double bond inside the ring. So how does a ring causes geometrical isomerism? We have already discussed. Now if there is a double bond inside the ring, in few cases I mentioned that double bond inside the ring does not cause us GI. So because we require sp3 hybridized carbon with two di substitutions, different di substitutions. Okay, but this is true only for smaller rings. For bigger rings, if there is a double bond inside them, double bond itself shows GI. Basically, carbon double bond carbon, the same way how in the normal straight chain shows cis and trans isomerism, same way in the bigger rings it tends to show the cis and trans isomerism. So in which kind of rings does it show GI? So GI is possible only when ring size is minimum 8 membered. So any ring below 8 membered, if it has a double bond is not going to cause any GI in them. Okay. Moreover, there are two different forms in which GI can exist. One is cis and one is trans. And some of the rings, cis isomer is going to be more stable than the trans. So in some rings, trans is going to be more stable than cis. So let's see first of all what are the cis and trans forms of a cyclooctene we have taken. This is cyclooctene. Now look at it very carefully. If I have placed a double bond here and if you mark hydrogens here, just look at these hydrogens. These hydrogens are coming. See, basically this is one carbon, this is another carbon. So another carbon chain is downwards and another carbon chain is also downwards. So if you'll just fix it like straight, what can you see? You can see this is a carbon, this is a carbon, here is the carbon chain attached, here is the carbon chain attached. So this is how the carbon chains are going, and hydrogen is upwards. And there is a double bond. So this particular form of cyclooctene, or this particular shape of cyclooctene where the double bond is here, is called as cis cyclooctene. Now cyclooctene can be written like this way also. Okay, so here if you look again, you have if I have taken these two carbons as the reference, this carbon has one R group down here, another R group down over here. So both R groups are down, so both hydrogens can be up, and this particular form will be called as cis-octene. Now look at the same structure, this structure, and try to see if we can form trans over here. What do we require for trans? One R group should be up and another R group should be down. Similarly, one hydrogen should go up and another hydrogen should go down. So instead of double bond being here, if I shift the double bond here, which I have done over here, this is one carbon in the reference and this is another carbon in the reference. Now look at the R groups, how it is attached to the R groups. One R group is going down and one R group is going up. Correct? Now hydrogens will be opposite to the R group. Okay. So if R group is going down, hydrogen will go up. If R group is going up, hydrogen will go down. So this is your trans cyclooctene. Here you have to mind one thing. What is that? Many people may ask, why can't we put hydrogen up? So let me draw a new cyclooctene and then explain you why hydrogen cannot be placed up. This is a cyclooctene. Okay. So here is my double bond. I have drawn it quite small. I think I won't be able to explain with this. Let me just draw it a little bigger. Very bad drawing I have. Can't help. Okay. It's a little distorted, but that's how it is. So there is a double bond over here. One hydrogen is placed over here. This is your R group. Now this is the another R group. And if I place one hydrogen here also, like this. Now look at the bond angles. Here the bond angle is approximately 120 degree. But do I have a bond angle of 120 degree over here or over here? No. If not, in that case, this hydrogen is going to feel a lot of strain. Why 120 degree angle or approximately similar angle is required? Because this is sp2 hybridized, right? So hydrogen, if I'll place at this position, it is going to feel a lot of strain. The angle is going to be a lot of angle will have a lot of angle strain. So it never places itself on at this upward direction. It places itself at downward direction whenever the double bond is formed over here. And that is why whenever the double bond will form over here, it will always form a trans shape. So hydrogen down, approximately 120-degree angle, right? So now this will stabilize the structure much better as compared to if hydrogen would have been up. So if double bond is here, it will form a trans shape. If double bond is here, it will form a cis shape, or cis alkene. So now accordingly, wherever you will place double bonds, you can see different places you can place. I have just taken two examples. You can take multiple different places where you can place double bond, and accordingly cis or trans cyclooctene can be formed. Now we'll take another example. Another example is cis cyclodecene. In this, again, if you look at these two carbons as a reference, and if I have put a double bond over here, the R group is going down, the another R group is also going down, and hydrogens will be up. This is the positioning of hydrogen, and this will be your cis cyclodecene. If I shift the double bond and if I put it here, now what is the problem? You have a R group over here, and you have these are the two carbons in reference. This is your R group and this is your R group. So R's are already opposite to each other. So hydrogen will be placed up, this hydrogen will be placed down, and this will be transcyclodecene. I cannot place hydrogen up. I cannot make this carbon, these two carbons as cis ever. Otherwise, there will be lot of angle strain on this carbon-hydrogen bond. Now, when I have taken two examples, one I have taken cyclooctane, another I have taken cyclodecene. In both cases, I have shown you cis and trans forms. Now, when we talk about 8, 9 and 10 membered rings, 8, 9 and 10 cyclodecene, cyclooctene, cyclononene kind of chains, here you will find, this is the common observation, that the cis forms of such cyclic chains are much stabler as compared to trans. Now, reason behind it, the reason is, first of all, cyclic chains have to twist a bit to form the trans kind of structure. Here, as the way I have shown it over here, it's not exactly that way. The chains are actually going, because this is the planar sort of structure over here. So they go non-planar first, and then they twist themselves, and that twisting of the bond to cause this transformation basically makes the system unstable. Even if you cannot imagine it that way, just try to see what I'm trying to explain you over here. So hydrogens, these two hydrogens are independent and just outwards in case of cis, whereas the hydrogen which is inside is going to face some of the repulsions from the downward R groups also. It is coming closer to the other downward R groups. Similar is the case over here. It is coming closer to the other R groups which are present over here. So it is going to face small amount of repulsion, whereas these hydrogens which are upwards, which are open in the space, they are not going to face any repulsion. That is the reason why cis is much stabler than the trans, especially in case of 8, 9, 10 membered rings. But if it comes to 11 membered ring and 12 membered ring, so angles will be quite large, and we want to reduce the angle strain by twisting them. So trans forms will be much stabler than the cis forms. So cis is better in 8, 9, 10 membered chains, whereas and post 11 or after 11, whatever the bigger chains are. So in trans form, basically the twisting happens in case of bigger cyclic ring also, and that twisting actually decreases the angle strain, and hence trans becomes much more stable than cis. In case of cis, the repulsions are more. Okay, how and why, that we can see only by making the structures. The structures of 11 membered chains and 12 membered chains are not as simple as these. Those are bigger and more twisted kind of structures, where cis tends to face a little more repulsion than the trans. Okay, so this you can just act as a matter of fact, because we generally deal with 8, 9 and 10 membered rings only. This is just for your information. Now there is one more example which doesn't have a double bond but is based on the cyclic ring. So I thought I'll just add it over here. That is decalene. Decalene is this structure. Okay, where decline or decaline, whatever you want to call. And in this structure, this question has been asked in JEE mains exam quite a long back. And what they asked, whether this molecule can show geometrical isomerism or not. So definitely when you look at the carbons, sp3 carbons are there, but no two different di substitutions are there over here. But this specific positions, so ideally it should not show GI, but these two specific positions tend to show the GI, these two carbons, not because they have different groups are present and all that. Basically, it shows GI due to the hydrogen positioning. So hydrogen, if they are coming out of the plane in the same way, basically both are towards the viewer or away from the viewer. This kind of positioning is called as cis. This is specific case. Decalene is the specific case. Okay, it doesn't happen in other things. So its structure is in such a way that both the hydrogens will be either coming up or will be going down. If they are both coming up or going down, the molecule will be called as cis. Whereas if one is coming up and one is going away from the viewer, the hydrogen, these carbons hydrogen, then this will be called as trans. So these are some specific cases which I'll be mentioning time to time wherever it is required. So this is about GI due to double bond inside the ring. Okay, now I think I had missed a small point when we were talking about carbon double bond carbon showing GI, and that I'll discuss now. So now one small point which I missed when I was talking about C double bond C system, and that was, so we discussed that there should be two different substitutions on carbon double bond carbon with respect to each carbon. Each carbon should have two different substitutions, so that can show GI. But apart from that, there was one more condition, and that was if we have two same groups which we are referring to see the cis and trans, in that case the distance between these two must change in cis and trans forms. What do we mean by that? Let me just explain you. Let's say, so this is my carbon double bond carbon, and these are two CH3 in the cis form. So whatever the distance between these two from here to here, whatever the distance is, that is L1. Okay, that is certain distance. And now if I shift it to this side, or let's say if I would have kept it like this, okay, and there must be some distance between this and this over here. Okay, that distance. And if I talk about these distances, this is how the distance is. Okay, so if I have kept, though don't treat it as a cyclic thing, assume this is one carbon, this end is one carbon and this end is one carbon, or I can take this as a thing, this is carbon double bond carbon, and this is one CH3 and this is another CH3. So this is carbon double bond carbon. If I keep it like this is cis. If I keep it like that, this is trans. So if you talk about the distance between this blue and this blue, it will be one distance, it will be some distance, let's assume this is L1. And if I keep it like this, there will be distance from here to here, and that will be L2. That will be L2, right? So these distances are not same. If the distances are not same, that means your molecule can show GI, or your molecule is showing GI, and these two forms are, one is cis and another is trans. If the distances become same, in that case, the molecule is not showing GI, as well as this carbon double bond carbon is not showing GI. Okay, so this is what exactly we are talking about. So here I have drawn the same structure, C double bond C, Me over here. So L1 is the distance between this methyl group and this methyl group, and here is methyl on the trans position. So this is L2. Till the time L1 is not equal to L2, 1 and 2, group 1 and 2 will be showing GI. As soon as this L1 and L2 will become same, then it will not show GI. So you may feel that in all the cases it will be different. No, it will not. We will discuss the cases where this L1 and L2 is going to be same and the molecules will not show GI also. Okay. Now one more example I forgot to tell you when we were talking about the cyclic structure showing the GI. And that was all the structure which I made were made up of carbon only. So it is not mandatory to have carbon over there in the cyclic ring to show the GI. You can have any other element also. So I have taken nitrogen here. So 1, 2, 3, 4, 1, 2, 3 and 4th position is nitrogen. Here in this particular carbon, there are di substitutions, two different substitutions. One is CH3 and another is hydrogen, and then rest of the group is same. Here the other atom which has two different di substitutions is nitrogen. One is CH3 over here and another is lone pair. So even lone pair will be treated as a functional group or a different group, and we'll be taking it into the consideration for finding out the GI. Okay, so now let's see whether it will show GI or not. So it's like basically this is the molecule, this is your carbon and this is your nitrogen. Okay, this is your molecule, this is planar molecule. So here if I place CH3 here and if I place CH3 over here, okay, this atom is nitrogen here, this and this atom is nitrogen, but these are two CH3s facing towards each other. So this is going to be your cis, and if it is facing downward, that is away from the viewer like this, then it is going to be trans. So irrespective of all the four carbons, all the four positions or all the positions of your cyclic ring are carbon or non-carbon atom, it really doesn't matter. The only thing what we need is that it should be sp3 hybridized and it should have two different groups present on it to show GI. Okay, so next I'll give you some questions. Try to find out the different stereoisomers in that. What all the number of stereoisomers are there if the molecule shows GI. So first thing you will find out whether it shows GI or not. Second thing, you will tell me how many stereo centers are there in that molecule. Now note down these questions and try them out on your own, and then I'll discuss the answers. So now let's talk about whether the molecule can show GI or not. Look at these two carbons. First we'll talk about these two carbons. So there are two different attachments over here. Two hydrogens and CH3 and one cyclic ring. So this has individually, each carbon has two different groups. So yes, this can show GI. So this is first stereo center. Now this is a cyclic ring, 8-membered ring with a double bond over here. Okay, so basically this cyclic ring will also show GI. Okay, and this is your second stereo center. Then come to the third one. Here double bond carbon. Basically two different chains altogether are there on both the sides, and hydrogens are there with a double bond. This will show GI. Let's talk about this. This carbon doesn't have two different groups, so this will not show GI. So total number of so according to this, there are 3 stereo centers. But just look at this thing also. In this particular position, these are two sp3 hybridized carbons with two different attachments. Two different attachments as in two disubstitutions. One is hydrogen, another is other group. So with respect to double bond also there will be GI, and with respect to the normal ring also there will be GI. So this ring itself will have two different stereo centers. One is the carbon double bond carbon, and another is the normal ring. Okay, so total stereo centers in the molecule are 4 stereo centers. I'll explain it again. So what is happening? In first, this is a normal stereo center. This I don't think anybody would have doubt. In the ring, there is a double bond which is causing stereoisomerism, and the sp3 hybridized carbons with the two different groups are also causing stereoisomerism. That is why these will be considered as 2 stereo centers. So total number of stereo centers in this chain is 4, and yes, it shows GI. So 4 stereo centers. Let me bring a different color pen. Next, question number 2. This will show GI. Yes, 2 different groups are present, so 1 stereo center is this. Will the double bond inside this ring will show GI? No. These double bonds will not show GI. Will these 2 carbons, sp3 carbons having 2 different attachments can show GI? Yes. So 1 stereo center is your ring. Then carbon double bond carbon with 2 different attachments can show GI? Yes, this can show GI. So this is another stereo center. So total number of stereo centers are 3. Come to the next one. Again, these carbons, this group has 2 different attachments on each carbon, so this will show GI. Then this cyclic ring will show will this cyclic ring show GI? No. This is sp3 hybridized carbon and this is sp2. Double bond inside the ring, anything smaller than 8 will anyways not show GI. So this ring also will not show GI because one is sp3 carbon and another is sp2 carbon. The next is, will this show GI? No. Why? Because this carbon has 2 same groups attached. So only 1 stereo center in this chain. Okay, so this is how they ask you question in the competitive exams also. They'll give you chains and they'll ask you how many stereo centers are present in this carbon chain. So you just have to see which all part of your chain are causing stereoisomerism, and that will be considered as stereo center. So now we'll talk about next few complicated cases of carbon double bond carbon where the stereoisomerism occurs, and those are some special cases also of carbon double bond carbon. So we'll talk about cumulines and other chains. Okay, so now let's discuss the other special cases of carbon double bond carbon. So now next we'll see GI in some special cases of carbon double bond carbon, as I mentioned. So the first such case is cumulines. What exactly are cumulines? Cumulines are polyalkenes in which you have consecutive double bonds. Okay, consecutive means the carbon is making double bond with one carbon here and one carbon. I mean, basically it is making double bond with the neighboring carbons, both the neighboring carbons. So that's how, if you have in series double bond, double bond, double bond, double bond, consecutive double bonds, that is called cumulines. So now, so in a chain you can have 2 pi bonds, you can have 3 pi bonds, you can have 4 pi bonds, and depending upon that we divide the cumulines in 2 categories. One is even cumulines and second is odd cumulines. So what is even cumulines? When the number of adjacent pi bonds are even. Basically, if I have 2 double bonds in the adjacent positions, then it is called as even cumuline. 2 or in the multiple of 2, then it is called as even cumuline. If we have 3 or multiple of odd 1, 3, 5, 7, like that. If we have pi bonds consecutively, then these are called as odd cumulines. Now let's see what exactly do we mean by even cumulines. I have CH2 double bond C double bond CH2. So basically I have one pi bond here and another pi bond over here. So basically 2 pi bonds. So, and the first carbon is sp2 hybridized. The center carbon, which is basically carrying 2 pi bonds, is sp hybridized, and again the last one is sp2 hybridized. This is the smallest. This is the smallest compound which will act as a cumuline. Basically, it will have a consecutive double bonds. Okay, and this is also called as allene. Okay, and this is also an even cumuline because it has 2 pi bonds, 2 adjacent pi bonds. Now, similar way, we will have the cumulines which will have odd pi bonds, and to understand which of these cumulines will show GI, we need to understand their orbital diagram. So let's talk about the orbital diagram right now. So now, this is, let's assume these are the 3 carbons which will be in the same plane. So I have just marked them in the same plane over here, and now I don't know whether you remember this or not, but we had discussed similar kind of orbital diagram in the class also. So basically this carbon is making a pi bond with this carbon, so there will be a p orbital over here and there will be a p orbital over here, so p overlap will be there. Okay, and p and sigma pi and sigma bonds are perpendicular to each other. Correct. So assume I'm assuming 2 planes. I'm taking 2 planes to explain this diagram. One is plane which is parallel to the board, or you can say when the things are in plane of the board, and one is perpendicular to the board. So assume right now the bond which I have made is in parallel to the plane of the board. So this is like, let me take an example over here. So now this what I have drawn, I have shown it here also. If you carefully look at it, these all 3 carbons, the purple carbons are sp2 hybridized. The purple carbons are sp2 hybridized, whereas the yellow carbon is sp hybridized carbon. Now this is the this is the p orbital, assume, and this is the another p orbital. I hope you can see this. This is the another p orbital. So these will have an overlap. Correct. This and this will form 1 pi bond. So purple thing is 1 pi bond, is forming 1 pi bond. So another p orbital which is going to form pi bond with the next carbon has to be in the perpendicular plane with respect to the above pi bond. So this plane has to be perpendicular to the board. If this plane, if black plane or this purple plane is parallel to the board, then this blue plane or the white plane with respect to this is going to be perpendicular to the board. So that's how I have shown. So this is one p orbital and this is another p orbital, and they will be overlap between this and this. I'm not sure whether you guys can see this properly or not, but again, so this is one, these two are making 1 pi bond, and this is making another pi bond. So 1 pi bond is in parallel to the 1 pi bond p orbitals are parallel to the board, and another pi bonds p orbitals are perpendicular to the board. Similarly, if you talk about the sigma bonds which are formed by this carbon, that is with 2 hydrogens, those are going to be perpendicular to the board. So these two are perpendicular to the board. These two are perpendicular to the board plane. Board plane is like this and this is like this. So this is going to be perpendicular. So these two are perpendicular to the board. One is towards the viewer, this is towards the viewer, and this is away from the viewer. If you are the viewer, this is towards the viewer and this is away from viewer. This is how exactly I have drawn it over here. Okay, now look at the last carbon. Now in the last carbon, what is happening? So if this pi bond is going to be perpendicular to the plane, this pi bond, so basically this blue things which I have shown you, this is going to be perpendicular to the plane. So what is going to be in parallel with the plane of the board? That is your hydrogen. So these hydrogens are going to be parallel to the board. So this is parallel to the board. These two hydrogens are parallel to the board in the same plane as the board is. Okay, just look at it very, very carefully again. So what is happening? These are the 3 carbons. This is sp2, this is sp, this is sp2, this and this is 1 pi bond which is in parallel to the board. This is perpendicular to the board. So sigma bonds are perpendicular to the board. The another pi bond is going to be in the perpendicular plane to the board. So this white this double thing and this this thing is also representing the p orbital. So this and this is overlapping and forming the another pi bond, and next set of hydrogens are going to be in parallel with the board. So exactly the same way how I have drawn it over here. So what we can see is, if I talk about the first carbon, so if I talk about the first carbon's hydrogens are perpendicular to the board. So first carbon's hydrogens are perpendicular to the board, whereas the last carbon's hydrogens are in parallel to the board plane. I hope you have understood this. Now, why do I require this? I'll tell you. Now, this is the orbital diagram of your even cumulene. I'll show you the orbital diagram of an odd cumulene also, and then I'll tell you how it shows the GI. So let's draw the another odd cumulene. Now what I have done is I have taken another odd cumulene, that is CH2 C double bond, CH2 double bond C double bond C double bond CH2. So how many pi bonds are there? 1 2 3. So this is an odd cumulene. Now let's see the orbital diagram of this also, so that we can understand and relate the GI related stuff with these two structures or similar structures with the longer chains, basically more even numbered cumulines, not even numbered, basically even pi bond in which they have, or even cumulines or odd cumulines. Now I have carbon, double bond carbon, CH2. Now one thing which without even looking at the orbital diagram, what you have to understand is that there will always be a sigma bond between this and this, right? So these sigma bonds are being formed between the first carbon and the second carbon. So one set of p orbitals will be forming a pi bond. Now this carbon, the second carbon, is forming the pi bond with the third carbon also. So that third carbon, when it will make pi bond, it cannot use the same plane p orbital. Instead it will have to use the another plane p orbital. So basically this carbon has used its one p orbital to form the pi bond with the first carbon, and it will use the another p orbital to form the pi bond with the adjacent carbon. So basically now this let's assume this red one was in parallel to the plane, this p orbital was in parallel to the plane, this blue one is perpendicular to the plane, because these both p orbitals will be perpendicular to each other. So if one it is in parallel to the plane of the board, the blue one is going to be perpendicular to the plane of the board. So these will form the pi bond. Now this third C is again forming a pi bond with the next CH2. So again this will be using another p orbital. So let's draw the another p orbital. This is my another p orbital, and it will be forming the pi bond. So now just look at it very carefully. So the first carbons and the last carbons p orbitals are in the same plane, or you can say this first two carbons and the third and fourth carbon, when they are forming the pi bonds, they're using the same p orbitals, whereas second and third carbon is using a different plane p orbitals, correct? So now when you'll talk about the two hydrogens, what the first carbon bond has, that is sigma bond, and that has to be perpendicular to the plane of the p orbital. So if p orbital of this red one, let's say this red is parallel to the board, blue is perpendicular to the board. Okay, so now if I have used red as one plane, so now if I have to show my sigma bond, I'll have to show with the another plane. So my another plane will be this hydrogen, and this is this, correct? Now look at the last one is also using the p orbital of the same plane. So basically both the hydrogens will be in the different plane now. So that will be, again I can write it like this. That's exactly what I have made over here. Okay, so what I have done over here, first carbon 1, carbon 2, using the p orbitals parallel to the plane, so the sigma bonds of it is perpendicular to the plane. Then second carbon and third carbon using pi bonds, forming pi bonds using the p orbitals perpendicular to the plane. Okay, and third carbon and fourth carbon again forming pi bond with the p orbitals in parallel to the board, and again these two sigma bonds are perpendicular to the board. So the same thing which I have explained you just now over here, now I'm explaining you with the orbital diagram here, the 3D picture. Okay, so now just look at it. So assume this is carbon 1, this is my carbon 1. Okay, let me just hold it properly. This is my carbon 1. I hope you can see. So this is one pi bond and this is the another pi bond. Not pi bond, sorry. This is the one p orbital. This is the another p orbital. This is hydrogen, which is perpendicular to the plane of the board, and this is parallel to the plane of the board. So these two are making pi bond. Okay. Now next, second and third carbon. This is second carbon. This is the third carbon. They are going to form the pi bond again, and that pi bond has to be formed through a different p orbital which is perpendicular to the earlier p orbital. So this was the earlier p orbital, now this is the perpendicular p orbital. So this p orbital and this p orbital is going to make a pi bond. Okay, now third and fourth carbon has to make a pi bond, and for that they need a different p orbital that is again perpendicular. So I had used these two orbitals, these two p orbitals to form a pi bond. So now third and fourth will make again the pi bond using this parallel to the board wala p orbital. So this is parallel to the board, this is also parallel to the board, and they'll form the pi bond. So now because this is parallel to the board, again the two hydrogens which are sigma bonded, so will be perpendicular to the board, right? So the first two hydrogens are also perpendicular to the board, and last two hydrogens are also perpendicular to the board. So what we have understood through this is, if we will take an even cumulene, so whatever the groups are present on the first carbon in the even cumulene will be in a different plane with respect to the groups present on the last carbon of the even cumulene. Here it was two hydrogens. These two hydrogens were perpendicular to the board, and last two hydrogens are parallel to the board. Okay, if we will take odd cumulene, the first carbon will have two groups attached to it. Right now here we have two hydrogens, so these will be in whichever plane the last carbon's two groups will also be in the same plane. So this is perpendicular to the board, this is also perpendicular to the board. Again we will see it through this is perpendicular to the board, and the last two are also perpendicular to the board. So here I had taken two hydrogens. We can have any other group also present over here, and accordingly we will just place it over here. But the whole idea is that in even cumulenes, first and last carbons groups will be in different plane. I have shown you the smallest cumulene, but any cumulene you will take, the structure is going to remain in the similar fashion. Okay, similar way, if I'll talk about the odd cumulene, groups attached on first and last carbon will be in the same plane. Okay, now how this information is useful, how it will help us in understanding GI of these compounds, let's see. Now let's say if I change the molecule structure a bit, and instead of CH2 I write CH3, and here also I write CH3. So as I mentioned earlier also, that any two groups can be attached over here. So I can write CH3 here, and I can write CH3 over here. That is the only change what is required. Okay, so now so we will be looking for the cis and trans thing, not for the center stuff which is carbon double bond carbon double bond carbon. That whole chain will not help us in figuring out the GI. Only first and last carbon will help us in knowing the GI well. Okay, or to figure out whether the isomer is cis or whether the isomer is trans. So in between, whatever the number of carbons are, those will not play any role. They will be just passive spectators. So because all of them are on the same plane and they don't have any group present on them, which can help us in making the GI or different isomers of GI. Okay, so this is the structure. Okay, now again let's talk about this structure on the carbon chain. So what I have done is I have taken this again, same odd cumulene. Now instead of let's hold it this way. So instead of a hydrogen, I'm just going to replace it with a CH3. Let's say I have taken CH3 as a green ball. Okay, so this is my CH3, this is my CH3. Now if you remember, when I was discussing about this carbon double bond carbon double bond carbon conditions to show GI, at that time I told you one is that the groups carbon double bond carbon should have two different groups attached on it, and second condition was that the distance between the same group should be different in both the isomers. Okay, so now please look at this molecule again carefully. So now both of the hydrogens are away from the viewer, that is I'm talking with respect to you. So if you are looking at the molecule, this is towards you, and the these hydrogens are away from you. So both of the hydrogens are towards you, so are in the same plane or in the same direction, both of the CH3s, correct? So this distance between this carbon and this carbon is going to be L1. The distance between this carbon and this carbon is going to be L1. Now if I rotate, not exactly rotate, yeah, if I shift the position like this, now what's going to happen? This is towards you, this CH3 is towards you, and this CH3 is away from you, correct? And now the distance between this carbon and this carbon is going to be different. Just look at it, this carbon and this carbon distance is going to be different, it is not going to be same. So when both were towards you, at that time the distance was L1, and when both one is towards you and one is away from you, these two CH3s or these two hydrogens, anything you can take it as a reference, the distance is going to be L2, and these distances are not same. So what I can say is, if I have to draw, let's say, the structures over here, and this is hydrogen, this is CH3, let's say this is CH3, and this is hydrogen, and there is a sigma bonding here. This is one structure, this is your cis structure, and this is your trans structure. And when I'll talk about the distance between the groups, distance from here to here is L2, whereas the distance from here to here is L1. Basically distance between the same groups we are going to check. This is L1 and this is L2, and L1 is not equal to L2 in case of odd cumulines. What does it shows? It shows that odd cumulines tend to show the geometrical isomerism. And how it shows, I have already shown you this. So this form of it will be called as transform, when one group is facing towards you, another group is facing away from you, right? And if both are facing towards, or if both are in the same plane, basically or same direction, both CH3s are towards you and both hydrogens are away from you, this will be called as cis form. Now let's see whether the same thing can be shown by even cumulines or not. Now let's suppose if I make the same change in the molecule of even cumuline, here I had taken two hydrogens and two hydrogens over here. Now let's say I make one as CH3 and another also as CH3. What will happen? Will this molecule show GI? Because we require two different substitutions on the carbon to get cis or trans isomers. That's the reason why we are putting one hydrogen and another CH3, just to see whether it will show GI or not. If it is CH2, it will not show GI. It will not make any difference in the molecule. Okay, so let's see again. So this is my even cumuline. My bad, I need to just move it a bit. So this is my even cumuline. This is one pi bond, this is the another pi bond between, this is the first carbon, this is the second carbon. Both of these p orbitals are, cut this whole part, okay? So this is my first carbon, this is my second carbon, this is a p orbital parallel to the board, this is another p orbital parallel to the board. Both of them are forming pi bond, correct? Now these sigma bonds are perpendicular to the plane of the board. Okay, so this is one CH3 and this is hydrogen, this is CH3 and this is hydrogen. This is what I have represented. This is the first carbon. Look at the second carbon. Second carbon has one p orbital in parallel to the plane of the board. So this is that thing which is forming a pi bond, and one p orbital which is perpendicular to the plane of the board. So this is the another p orbital. Now look at the third carbon. Third carbon has the is forming its pi bond using the p orbital which is perpendicular to the plane of the board. So this white one and white one are forming the pi bond. So basically whatever the sigma bonds are going to form in the 90-degree angle with respect to this p orbital. So this is my 90-degree angle, and this is parallel to the plane of the board. So I have what? I have a CH3 over here and hydrogen over here. I have mentioned CH3 over here and hydrogen over here. So basically according to the diagram, the CH3 should be up. So if I'll rotate a bit, I think it will be this. Yeah, so this is exactly what we are expecting. This is the structure of molecule in 3 dimensions. This is how exactly it will look like. Now we have to figure out whether changing the positions of CH3 either way, either in this position or this position, is going to make any difference in the distance between one CH3 and another CH3 or not. So basically this is your CH3. This is like this diagonal. Look at it like this. This is one CH3, and the distance between this CH3 and this CH3 is going to be L1. This CH3 and this CH3 is going to be L1. This is how it is. I don't know whether I can put a scale or not. I have a scale or not, but let me just see. So basically this is the distance. That's how I'll measure the distance. It's not a straight thing. It's not one straight thing. It's little diagonal. Not exactly diagonal also, but little diagonal. Yeah, so this is how it is. Correct. So now if I'll rotate this carbon and bring the CH3 down, so basically instead of CH3 being here, if I bring the CH3 down, the distance is this, again diagonal, but distance seems to be same. From here to here also distance seems to be same. So no matter we are changing the position of CH3, the distance with respect to the another CH3 is not changing. We are not changing the plane. Basically we are changing where it is facing right now. So earlier it was facing up and now it is facing down, but changing the face of the CH3 is not changing the distance between one CH3 and another. This is L1, and if I rotate it, this becomes L2, and L1 and L2 is exactly same. So basically in case of even cumulines, what we have seen, L1 is equal to L2. Distance between, I am drawing it in the same diagram, you have to draw it in a different diagram. So this is your L1, the distance between one CH3 and another. If I move it down and write it like this, okay, even though in a two-dimensional plane it is looking like there should be some difference in the L1 and L2 angle, L1 and L2 length, but I have shown you just now, even though this, if I talk about, this is not straight, this is also diagonal, this is going down, right? So this L1 and L2 are going to be same. So just remember this thing, that you don't have to, every time when you get a question, you don't have to draw the structures like that. What you have to understand is, even cumulines do not show GI, whereas odd cumulines do show GI. Odd cumulines means odd number of pi bonds, adjacent pi bonds we should have. So odd cumulines always will show GI because their L1 and L2 length will keep changing when you will change their positions. Not exactly positions, but their arrangement. But when you talk about the even cumulines, even if you change the position of the same group, not exactly position, but the alignment or the arrangement of the same group, L1 and L2 is still going to remain same, because these two are in two different planes, and two different planes, no matter you rotate the carbon, still the distance from the earlier CH3 will still remain the same, and it will not show GI. So you don't have to think much while marking the answer. Just look at it, what cumuline it is it even or it is odd? If it is even, no GI. If it is odd, it will show GI. But to show GI for odd cumulines also, you should have two different groups on the first and the last carbon. You cannot have the same two same groups, and if it is like two hydrogens or two CH3s or anything like that, it will not show GI. So all these things you have to keep in your mind. Note this down, and then I'll do some questions on it. So now let's see these questions, whether these compounds can show GI or not, and if they can show GI, how many stereo centers do we have? So look at this first carbon double bond carbon, two hydrogens, and then two other groups are present over there. So basically two different groups are present, so this will show GI. correct? Now look at the next part of the chain. So this looks like a cumulene. So how many double bonds are there? 1, 2, 3. So it is an odd cumulene. So odd cumulenes generally show GI. Now we have to check whether we have the on the first and last carbon, do we have two different groups attached or not. So this carbon, this is the first carbon of the cumulene, so it has one hydrogen and one CH2 attached to it, two different groups. And this is the last carbon, so it has one hydrogen and one CH3 attached. So we can see cis and trans with respect to the hydrogens, correct? So this will also show the GI, this part will also show the GI. So this will be considered as one stereo center. One stereo center was here, another stereo center was here. One cumulene, the total chain of the cumulene will be considered as one stereo center. So total number of stereo centers are 2 over here. Okay, 2 stereo centers. Now come to the next. Again, look at this carbon, double bond carbon. So it has two different groups attached. One is hydrogen, one is this big chain. Here it has chlorine and hydrogen. So we can see cis and trans with reference to the hydrogen. This will show GI. Look at the next part of the chain. So this seems like a cumulene. I have 1, 2, 3. 3 pi bonds, odd cumulene. Now I have to check whether it has two different attachments or not. This carbon, this is the first carbon, this has one hydrogen, another is CH2 and the rest of the chain. This has one hydrogen and one benzene. So basically two different groups on each carbon, first and the last one. We can see cis and trans with respect to the hydrogen over here, and this will also show GI. So basically two stereo centers. Look at the third one. Third one seems like only cumulene structure. So this has 1, 2, 3 odd number of again odd number of pi bonds. So odd cumulene, and it has two different groups present on the first carbon and the last carbon. So it will show GI, and it has only one stereo center. One stereo center. Okay, now one thing you have to understand is, now we have done cumulenes. Now similar way we can have the structures where we will have, instead of double bonds, we will have cyclic rings and the spiro rings attached to each other. So basically something like this. Wait, something like this. One ring is attached to the another ring, and then further rings, so on, and then the carbons attached to it having the H and CH3, and the carbon of it has H and CH3. So basically this kind of structure is also we are going to discuss. If we have any spiro chains and the carbons of those spiros have the two different groups attached to them, whether such kind of chains show GI or not. So we will discuss about these spiro chains now. Next, always remember one thing, cyclic chains and double bonds are equivalent to each other. So the way how double bonds behave, the same way how spiro or any cyclic rings behave. Okay, why I'm telling you this, because you will find the orbital diagram of these spiro based compounds very similar to what we have done in the case of cumulenes. Okay, so let's see some of the examples of spiro based compounds and see whether the GI, whether these can show GI or not, and if they can, in what all conditions, if they cannot, in what all conditions. Okay, so now we'll discuss about cycloalkylidenes, which is again one of the cases of carbon double bond carbon, some weird cases where we have to figure out whether GI happens or not. So cycloalkylidenes, so what are these compounds? The compounds which have some cyclic chains, then double bonds, and again cyclic chains, and then double bonds, and so on. So basically the carbons on the cyclic chain are also forming a double bond with next carbon. So basically carbon of a cyclic ring is participating in forming a double bond, and then there is another carbon which is present next to it, which may be the part of a cyclic ring or maybe an independent carbon altogether. So cyclic chains carbons, when they form double bond with the rest of the chain, such kind of compounds are called as cycloalkylidenes. Okay, so now again here we have the cases like spiro and cumulenes. Here also generally what we see is the cycloalkylidenes is the combination of cyclic ring, then double bond, then cyclic ring, then double bond, then cyclic ring, then double bond, and so on. Okay, again here the number is odd and even. Odd and even basically depends upon how many cyclic rings and double bonds are there. I told you earlier also that the double bonds are equivalent to cyclic rings. So if I say I have one cyclic ring and one double bond, that means I will consider that particular compound as even compound or even alkylidene. Whereas if I have one cyclic chain, then a double bond, then again a cyclic chain, basically 3 times the things are repeating, 2 cyclic ring and 1 pi bond, and that will be called as odd cycloalkylidene. Okay, so let's see the first example. First example is this. I'll just draw the normal form of it, and then probably we will try to understand. This is my compound. So here where there I have a cyclic chain and a double bond. So basically this is an even cycloalkylidene, one cyclic chain and one double bond. Now we will see the not exactly orbital diagram, but yeah, somewhat orbital diagram of it. We will try to see how in different planes the things have been distributed, so that we can figure out whether GI can happen or not. Now remember again, before I start explaining this, that the terminal carbon groups of such cases, if are on the same plane, then they tend to show the GI, because their L1 and L2 will be different. If they're in the different plane, then the L1 and L2 is going to be same, and hence they do not show GI. This you have to keep in mind before learning all these cases. So now here, let's look at it. The cyclic chain is in one plane, that is plane parallel to the board. Now the sigma bonds, what it is forming, this sigma bond, let's say whatever the plane of this chain is, these sigma bonds will be perpendicular to that plane. So if cyclic ring is in the plane parallel to the board, so if this is how the cyclic ring is, this is how your bonds are going to be, the CH3 and hydrogen. So one CH3 will be here and hydrogen will be inwards. So this is the perpendicular plane of the board. So now when we are talking about the pi bond, what is forming, pi bond will also be the perpendicular plane of the ring. So if this is the plane of the ring, that's how your p orbital, which will be participating, this will be your p orbital, which will be participating in the formation of pi bond. Okay, so everything is going to be perpendicular with respect to each other. So if this is parallel plane, then this is going to be a perpendicular plane. Then again, the carbon which is forming the pi bond in the perpendicular plane, its sigma bond will be in the parallel plane. So perpendicular, parallel, perpendicular, parallel. That's how it is going to be. Now look at the first carbon and the last carbon. Last carbon's attachments and the first carbon attachments are in the different plane. This is parallel to the board and this is perpendicular to the board. No matter, I had taken CH3. Now here the CH3s both are down, and here is one down and one up. Irrespective of that, these two set of groups are in different plane altogether. So no matter I talk about this first case or I talk about the second case, L1 and L2 is going to remain same, even though it looks like both are in one direction. They are not in one direction. They are basically in completely different plane. So one is CH3 like this and another CH3 is like this. So assume if this is the CH3, if this is the CH3, this is going to be another CH3. So distance between this CH3 and this CH3 is going to be a diagonal sort of distance. If I switch it over, then also the distance will remain same. Only thing is, right now we were finding out the distance from here to here. Now we will find out the distance from here to here. That's all. So L1 and L2 will remain same. So such kind of structures do not show GI, and I have written it a general statement over here: groups on the different plane. Here the groups which are present are on the different plane, and hence they will not show GI. Now let's talk about the second case, where I have taken this kind of structure, where I have a cyclic chain, then a double bond, then again a cyclic chain, and these are the terminal carbons where the groups are attached. So there is a CH3 over here, there is a hydrogen over here, there is a CH3 here, and there is a hydrogen here. So what kind of system is this? One ring, then double bond, then one ring. So basically it's an odd cycloalkylidene. Basically three different structures are attached to each other: cyclic ring, double bond, cyclic ring. I told you cyclic rings and double bonds are equivalent to each other. Basically they are considered equivalent to each other. So this is an odd cycloalkylidene. Now we will see the orbital diagram of it. If this is parallel to the plane, this is going to be perpendicular. The pi bond formed will be perpendicular. This will again be parallel, and this is going to be perpendicular. That's how the arrangement is going to be. So basically this set of groups and these set of groups are going to be in the same plane. So when they are in the same plane, when you'll switch their positions, the two CH3s are facing towards the viewer. When you'll switch it to up, and it will be away from the viewer, in that case L1 and L2 is going to be different. If L1 and L2 is going to be different, that means it will show GI. So what is the common observation in cumulines and spirines and cycloalkylidenes? That odd ones tend to show GI and even ones do not show GI. So that is what I have mentioned. Odd cycloalkylanes can show GI if each terminal carbon has two different groups attached to it. And a generic statement, if adjacent double bonds are even. Adjacent double bonds means we are talking about the cumulene right now. If cumulines are even or spirenes are even, and the ring and double bond combination is even, in that case such compounds do not show GI. You do not have to do anything at that time when you get such questions. You just have to see whether they're even or not, and you have to see whether the two different groups are present on the terminal carbons or not, and that's all. You just need to understand that the odd ones tends to show the GI and even ones do not. Okay, so this is about 3 cases. There are still few cases of carbon double bond carbon and the cyclic chains are left, and apart from that we are left with carbon double bond nitrogen system and nitrogen double bond nitrogen system and the generic formula to calculate the stereoisomers of a compound. So that we'll cover up in the next class. Till then, you make notes very properly. Make sure you write each and everything nicely, because these are important things. This topic what we are doing is still the advanced level, so you will not get any questions beyond what we have done. Whatever questions you will encounter with respect to geometrical isomerism will be from these parts only. Okay, now when I'll send you the third video, that is the last lecture of GI, that will basically cover up everything and the GI will be over. So what is my suggestion is, when you do the third video, you again go through the first video, second video and third video. First and second video in the faster pace and the third video with the normal pace, and then I'll give you a worksheet which you have to solve. If you'll directly start solving the worksheet, then you may get confused and you would have forgotten few things, because it took 3 weeks to finish off GI. Okay, so ideally, even when you are watching the second video, I would suggest you to go through the first video at the faster pace first and then watch this video. Or if you have already watched the second video, then again, just to revise, go through the first video, then again watch the second video, both of these videos in the super fast speed, basically 2x speed, and then be ready for the third video. Before watching itself, again see both of these videos, figure out if you have any doubt, and then go to the third video, because that will be the end of GI, and then we'll be starting the optical isomerism. If you are clear about GI, understanding optical will be easier for you. If you are not clear about GI, again optical is going to be little more three-dimensional kind of thing, and you have to understand. So basically you have to analyze the compounds using 3D picturization or 3D imagination. If you are not able to do so, you may not be able to have a good hold on the optical isomerism. So all that you have to keep in mind and do these things accordingly. These videos will be there on YouTube also for the later use. Basically you'll keep forgetting and then you have to watch them again and again. This is very, very important. So that's why we will just keep it. We will not delete them. And in fact, you can also keep the links with you so that you can later on use it for the reference whenever it is required. Okay, so next video I'll send you on next Tuesday or Wednesday mostly. Okay, this video, watch it, make notes properly, and I'll send you module as well as assignment both.